All right. So today we're going to be talking about three flavors of ways we describe fluids. That is the idea of control volumes, systems, and then the interplay between them, which is a thing known as the Reynolds transport theorem. We're going to build up to that and finish that next lecture, but we're going to get started on the process today by first defining what these systems, control volumes, control surfaces, what these actually are. These are things that you've probably seen a little bit of in thermo. Describe how the conservation equations that we're familiar with from earlier courses in physical science apply when we're talking about systems, control volumes, control surfaces. And then we're going to begin this march towards this Reynolds transport theorem by defining what we call intensive and extensive properties of a fluid. Before we do that, because this is going to be important in the stuff to come, I want to revisit or do a quick recap of this material derivative we discussed in the last lecture. Right? So remember that the material derivative of something is written as the partial time rate of change of that something plus the convective rate of change of that something. All right, whatever that something may be. We'll go ahead and write that as some quantity b that can be a scalar, vector, or anything, or a higher order tensor. So to make sure we're good with how we apply this, let's start out with a quick example problem. So assume velocity field in some body of fluid. We'll go ahead and call it a room full of air. The velocity field in a room is given by negative y z I minus x z j minus x y k. So it's a three-dimensional velocity field. Okay. At the same time, the temperature in the room is given by the following scalar field. So the question here is, if we were to release a very small, neutrally buoyant probe, something like a little, even a balloon. Let's say we have some sort of tiny little weather balloon that we release into the air so that it flows along with this velocity field and follows it as a tracer. Can we find the rate of change of temperature experienced by a tracer particle that's following this velocity field that we've been given? All right, so those of you that have been checking in on the ICON site, I did upload a couple examples that worked through very similar problems to this. And the methodology that I propose in this example is basically take your material derivative and expand it out, right? Get rid of this vector notation and write it as the dt of, well, we'll go ahead and write it down here. So dt is equal to the partial rate of change of temperature, okay, plus u dt dx plus v partial t partial y plus w partial t partial z. All right, so we've taken this vector expression at the top and we've just plugged in all of the relevant vector components. So what it comes down to then is just write out each of these components, u, v, w, and the partial derivatives of t with respect to time, x, y, and z, and put those in the table. Okay, so So we could write that u, the x component of velocity, right, is equal to negative yz. V, the y component of the velocity, is equal to negative xz, and w is equal to negative xy. We write that partial t with respect to time is equal to a times negative a times sine at. Partial t with respect to x is going to be cosine xy times x, times y. Partial t with respect to y, similarly cosine xy times x, and partial t with respect to z, z squared. All right, so take this, box it off somehow, and recognize that now here's your sort of list of ingredients that you can use to assemble the expression that's going to give you the material derivative of the temperature as witnessed by a particle following this velocity field. So simply plugging items in now, we can say dt with respect to time is equal to that first time derivative at negative a sine of at, okay, plus u times dt dx. That's this guy multiplied by this guy. So we're going to end up with negative xy squared cosine of xy plus v times the y derivative, so that guy and that guy can be negative x squared y cosine of xy plus, and then finally w times the z derivative, which is going to be negative x y z squared. Okay. And at this point, you could simplify things a little bit, right? You could factor out that cosine xy from the middle two terms. You could group terms however you want, but this is substantially correct. Now, that's all there is to it, to finding the material derivative. I wanted to remind you guys of this process, in case you didn't catch the examples that I put up on icon, but because this is going to be, right, understanding the material derivative like this is really going to help you moving into the end of this chapter and especially the next chapter, because it's this idea of saying, right, we're given a velocity field and a temperature field. Okay, they're field representations, meaning they're Eulerian representations of the velocity and the temperature. They're not specific to any particle. They're defined with respect to space and time. But what we're getting out of it, this big D t dt, the material derivative, is the Lagrangian rate of change experienced by a particle that happens to be at some location, x, y, z, and at some time. Okay, so it's a way of sort of moving from this field representation into a Lagrangian rate of change. Any questions on this example? All right. Let's move on to sort of in line with what I was just, what I was just saying is that the motivation today is we're going to be looking at another way we juggle this Lagrangian and Eulerian representation of a fluid. So first, a couple of definitions. Okay. A system is a collection of matter of fixed identity. Okay. Which may move, deform, or otherwise change as it moves through a flow or as it interacts with a flow. Okay, so the idea is that once you specify a set of molecules or a set of particles as a system, that same set of molecules is always going to make up that system. So a system like this that is also often referred to as a closed system, okay, where it's always the same set of matter, and it can also sometimes be known as a material volume. But we'll stick with system right now as the way we define this. So as an example, right, if you take a pot of water and you put it on the burner of your stove and you turn up the heat, right, you say that the water I put into this pot, okay, that is my system. And you put it on the stove and it begins to heat up, and some of that water begins to evaporate and turn into water vapor, right, which floats around the room. Maybe some of it gets sucked out by the exhaust vent. Okay, your system still has to include all of those original molecules, both the ones that are still liquid, the ones that are floating around in the room as water vapor, the ones that are now down the block because they got exhausted out of the house. Okay, all of those molecules have to be accounted for in the system. A control volume, on the other hand, is a region of space through which fluid may flow. Okay, so unlike the system, right, this is not matter fixed, it is geometrically fixed. And going back to the same example of boiling a pot of water, we might say that the pot itself, the interior volume of the pot, is our control volume. So as you boil water and water vapor rises, it is actually leaving the control volume, even though it remains part of the system. And then a control surface, on the other hand, is simply the set of surfaces that make up the boundary or the boundaries of a control volume. So one moment here. So I'm going to put those. All right, so this is an image that was used to demonstrate this idea in a class that I actually took once, and I thought it was a pretty good one. So if we consider like this image here of Mount St. Helens erupting in 1980, okay, if we referred to the actual matter that's making up this big cloud of ash and debris, okay, we could call this our system. Now, about a week before this image was taken, right, this same system was comprised of solid matter down below the surface of the mountain slope, right? And as time went on, this ash cloud spread over a huge percentage of the Earth, and there was ash located continents away. Okay, still as part of the same system. If we wanted to describe a control volume, though, okay, we might say, let's put a box around here and say that if we put this box that is maybe, I don't know, a couple miles wide or maybe a mile wide and a mile tall, and a mile deep, and we fix this on top of Mount St. Helens and use this as a frame for doing photography, or maybe we call it a containment region, right? Any ash contained within that box is not going to be a risk, a public health risk. That would be an example of our control volume, anything inside of it at an instant in time. And then finally, right, so that's the volume of the box itself, okay? But volume. But then this box has to be made up of 6 surfaces, which are going to be known as our control surfaces. And so the only way that part of our system can enter or exit the control volume is by crossing through a control surface. All right, so why do we care about this this difference between systems and control volumes? Well, I want you to think back to. Okay, I want you to think about classes you've taken in statics, dynamics, physics, right? Where you've learned, or thermodynamics, where you've learned what we call conservation laws, right? Conservation of mass, conservation of momentum, also known as Newton's second law, conservation of energy. Right, which are generally written, we'll go and say conservation of mass, right, which says that ddt of, well, that the total, there we go, the proper time derivative of m, the mass of something, is equal to 0, right? Conservation of momentum, which is known as, right, Newton's second law of motion. Says that the sum of the forces on something is equal to the time rate of change of the momentum of that something. And then conservation of energy, which says that the time rate of change of total internal energy is equal to, right, heat transfer in minus work out. Okay. Now, of these 3 things, right, systems, control volumes, control surfaces, what do these conservation laws apply to? You think back to saying the mass of something doesn't change, right? Is this going to be applied to a collection of matter? Or is this going to be applied to a region of space? It's going to be a collection of matter, right? Meaning this is stating that the mass of a system, a closed system, won't change. Right? So this m here refers to the cumulative mass of a system. Conservation of momentum, right? Sum of the forces on something. Generally, that something that we've been applying this to, okay, in dynamics and in physics, is going to be like a solid object. Consider a baseball, right? That baseball is always going to be made up of the same component, constituent particles, right? And so when we're applying F equals ma to that baseball, what we're doing is applying it to the system that makes up that baseball. So this also applies to a system. And then from thermo, okay, when did you apply this? This time rate of change of internal energy. Was this to closed systems, right? So we're talking the energy in a closed system. So this gives us a dilemma, right? Because these are like the fundamental laws of physics that we use as engineers to solve physics problems. But they're applied to systems, which are, if you haven't picked up on it yet, Lagrangian representations of fluid, right? Because they mean tracking all of the constituent pieces that started out defined as a system. So if you're trying to do conservation of mass, right, and you're boiling a pot of water, in order to apply conservation of mass to that system, you're going to have to track and keep track of every single particle that boils off, goes out through the ventilation fan, floats into the living room, right? It turns into mathematically a completely untenable proposition. At the same time, what would it mean to apply to something that isn't a system? What if that baseball problem, right? I can tell you, here a batter hits, right? A batter swings and hits a baseball with some amount of force. Find the acceleration of that baseball, right? When impacted by that force, that's easy, right? That's familiar. But what if I said the batter swings through a batter box, apply F equals ma to that batter's box, that region in space, it's going to be a nonsensical sounding idea, okay? Because you're not applying it to a physical thing. So that's what we're going to try to do in the next couple of days is figure out how we can apply these conservation laws to regions of space, because regions of space are a lot easier mathematically to keep track of and to work with than these floaty globules that we call systems in fluids. So we seek to apply conservation laws that are previously defined for systems which means that these are defined in a Lagrangian framework, okay, to control volumes, which means that we're trying to apply these now in an Eulerian representation. Okay, so let's return back to a set of slides here. Consider a case where we've got a fire extinguisher, and we're interested in applying conservation of mass to this fire extinguisher, or to the propellant and extinguishing chemical that's contained in it versus the control volume itself. So conservation of mass would tell us that, let's change the color of that, would tell us that ddt of the mass of the system, that is everything that's inside of the tank before the valve is opened, is going to be equal to what? 0, All the mass has to stay existent. Mass is not created nor destroyed. So here's our conservation of mass. Okay, what if we wrote, how would we define dt of the mass contained within the control volume, that is the internal volume of the tank, as soon as you open this valve? I'm just looking for a sign. Is it going to be 0, positive, negative? It can be negative, Because mass is leaving the tank, venting out to the atmosphere. So we're going to say this is negative, Okay, now if we define, though, this control surface here as this teal dashed line that sort of bounds the internal surface of the tank, rather than writing ddt, what if we said m dot cs? That is, m dot cs is going to be positive if mass is crossing into the control volume across the surface, and it's going to be negative if it's leaving across the control surface. Sorry, nope, I got that wrong. Backwards. Because we define the normal vector on surfaces as positive out. It's going to be positive if mass is crossing outward and negative if it's crossing inward. So in this case, we would say that the mass flowing across the control surface, or the rate of mass flowing across the control surface, is greater than 0. So we've got a comparison, System mass rate of change 0, and then we have the time rates of change of mass in the control volume and mass across the control surface have opposite signs. And what we're going to show next is that you can actually combine the second two terms, and these second two terms have to add up to 0. Okay, a few other examples of control volumes and control surfaces. So control surfaces and control volumes can be stationary, they can be moving, they can be rigid, they can be deformable. or any combination of them. The only idea is that they have to be defined using a spatial description or geometric description. So what we'll typically use in this class is known as a fixed control volume, something that stays put in space and fluid moves through it exclusively. An example is if you have a pipe and you say this chunk of the pipe, right, the internal volume between this point and this point will be my control volume. You're going to track flow as it moves through that totally stationary region of space. Other examples involve moving control volumes. The good example being this jet engine right here, where we would say the volume inside of the nacelle of a jet engine is going to be our control volume. Sure, there's flow moving through it, but it's also got a velocity of its own. Then we've got moving or fixed deforming control volumes. Examples often being things like balloons, parachutes, etc. The idea being that the boundaries don't have a simple fixed geometric shape, but they can deform more organically. And often, as in a case like this, the volume of the control volume is going to be somehow a function of how much mass or how much of the system is left inside of it. Okay. Okay. We'll move on to talk about intensive and extensive properties. What I talked about previously with the fire extinguisher and having the rate of change of mass and the control volume and the rate of change of mass, or the rate of mass flowing across the control surface. That's a little precursor to what we're going to formalize on the next lecture. So we're going to leave that on the back burner now and go and fill out some of the the remaining concepts so that we can get through that without any issues on Friday. So intensive and extensive properties are stated like this. If we let B, okay, represent a fluid property, that depends upon the quantity of fluid. Okay, what I mean by this is something like mass, okay, the energy, okay, the volume. Things where if you contribute more fluid into this accounting, then the value of B is going to change. Generally, it's going to increase. Right. And we let little b, I should say that this big B then is what we call an extensive property. We're going to let little b be or represent the amount of big B per unit mass. This is what we call an intensive property. So, for example, as a little example exercise here, if we list a set of extensive properties, mass, kinetic energy, maybe momentum. And we write, okay, that B is equal to, right, in this case, M, the mass itself. B is equal to 1/2 mv squared, and B is equal to mv. All right, familiar properties. The intensive properties that correspond to each of these. Right? What is the intensive property corresponding to an extensive property of mass? Well, it's going to be mass per unit. That would be mass per unit volume, right? But mass per unit mass is just 1. Okay, it's that simple. Sorry, that's a bit of a trick question. You simply say the intensive mass of fluid is 1. Okay, kinetic energy. Just divide out the m, 1/2 v squared. Okay, momentum. They're going to be v, right? The velocity. So this is a different way of thinking about how we describe the amount of a property in a per unit mass, where we could say, you know, the velocity of a fluid is also considered then the momentum per unit mass. So how do we write, okay, these extensive properties? Clearly, these are the things we usually apply conservation laws to, right? Conservation of momentum, conservation of energy, conservation of mass. So how do we apply these? How do we write these for a system? The idea is going to be, right, that B, the system, is basically going to be the limit as little volumes approach 0, with summation of I to the number of these volumes as they approach infinity of B I times rho I times delta V I. Okay, so all this is saying right here is if we divide our system into a bunch of little tiny volumetric chunks, each one has a volume of delta V with a bar through it, right? Delta volume. And each one of those has an associated density. If we take that rho times delta volume, we're going to get a little mass. And if we multiply that little mass for element I by B sub I, then we're essentially summing up all of the little elements of that extensive property. Okay, so if we have a rock, it is we could divide this up into a ton of, in the limit of an infinite number of little pieces, and each one, okay, we could say this has some little volume, it's got density, and it's got its intensive property. We multiply those things together, and then we do that for every little piece, add them up, we get the total extensive property. Right? But when we do this sort of thing, right, this is what we would call a Reynolds sum, right, where we take the limit of a summation for volume, and because we've all been through calculus, we should be able to recognize that this is usually written instead as V times rho D volume. Okay? So it's taking the little tiny volume multiplied by density, little tiny mass times intensive property, and adding them all up through this integration process to get the total amount of big B, or extensive property. So physical laws, right, such as Newton's second law of motion, typically take the form, right, of d dt of b system is equal to, you know, something, which we could write in this case as being d dt of the integral of the volume of that system of rho times b dv. What we want, and what we're going to get in the next lecture, and this is what I'm getting at, is that because we never are going to be able to track the volume of a system to be able to do an integral over it, okay, because systems move and they change shape and they are just generally not friends with the math that we use. So what we want is something of the form of d, right, b of control volume dt is equal to, right, something to the time rate of change of an integral over a control volume rho b dv. The problem is these two things are not the same. Okay, these two integrals, because the integration domain, volume of a system versus a fixed volume in space, right, they really have nothing to do with each other. So this is going to be the job of, again, said this thing called the Reynolds transport theorem that's going to allow us to apply this, these physical laws as written for systems using control volumes and control surfaces. As a preview, what the Reynolds transport theorem does, Reynolds transport theorem, right, intro here. Without any formal derivation, it basically says that the rate of change of big B in a system, okay, is going to be equal to the time rate of change of that B contained in a control volume plus the amount of B out through a control surface minus the amount of B in through a control surface. Okay. This seems like a really strange way to write it, but the advantage here is basically this is what most, right? B is momentum. Then the rate of change of momentum of a system is the sum of the forces on the system. So we can say sum of the forces on, right, that system can now be written using control volumes and control surfaces. And like I said, the next lecture we're going to get a little more formal with this. But for now, just give you a quick demo of what this actually looks like. All right, so okay, so here we've got that statement I just wrote down. This is the Reynolds transport theorem. Okay, that equation is what that's called. So I'm going to consider a case where these four green circles make up our system at some instant in time. All right, so we might say that B, right, is defined as, I don't know, we'll say that B is defined as the actual number of particles. B, small b then would be something really weird. It would be the number per unit mass. So I guess that would be what, the mass per particle? Anyway, if big B is the number of particles, obviously if you add a particle to it, B increases, so that's an extensive property. If we want to track the rate of change of the number of particles, okay, the idea is as these move, if we assume that no particles get destroyed and no particles get created, these four particles that are green should stay in existence, right? We should always have four in our system. So if we step forward, as the flow is moving from left to right, if we step forward, okay, we've still got four particles in our system, right? It's not colored green anymore, but those four particles still exist. But what have we done? We've got now our control volume, which is this pink region here, right? Our control volume, and then we've got our control surfaces, make up the edges here. What's happened to the number of particles in our control volume? It's decreased by 1, right? There's only 3 particles in that pink space. So we would say that the rate of change of particles in the control volume could be read as -1. Okay, how many particles have left the control volume by crossing a control surface? Just that blue guy. Right? So we would say that's 1. And how many have entered? 0. Okay, so we know this is 0, and all we're doing is confirming then that the only change in the control volume is due to flow across the control surfaces. Okay, this is all the Reynolds transport theorem is doing. It's bookkeeping. If we step forward another time step, okay, what's happened since the last one? So before we had, right, we had -1, we had 1, we had 0. That was time step 1. Here we've still got 0 for the system change. Now we've added a particle to our control volume, so that goes back +1. None have left, so that's 0, and 1 has entered, right? So we're going to end up with 1 there, right? So in both cases, the right-hand side equals the left-hand side. And then third time step here, have any entered? No. Have any left? No. And has the number of particles in the control volume changed? No. So we would have 0, 0, 0, which of course sum up to 0. So this example is simply to demonstrate that, in fact, we can, right, just to seed that belief in your head that we can write the rate of change of something about the system, okay, which is flowing with the fluid. Okay, the system is now made up of, the system is now made up of these particles here, which are no longer coincident with the control volume. But we can track the rate of change of some property of the system using a fixed region of space and the control surfaces that bound it. Okay, and we actually got through that a bit quicker than I expected. That is all that I have for you guys today. So we're going to end this a little quick. Reminder, midterm info, again, right? Friday, it's going to be over in the Papa John building, W10. That's the big 380-something seat lecture hall. Materials you're allowed to bring. Remember, we're covering lectures 1 through 10. That's chapters 1 through 3. That goes from fluid properties up through Bernoulli. And come chat if you've got questions.